Hello and welcome to session 4 of Unit 2. This session is going to introduce you to nuclear activities and transmutation. By the end of this session, you would be able to explain nuclear activity and you will also be able to explain nuclear transmutation. Let us start by looking at activity. The activity of any radioactive decay or radioactive process can be defined as the number of disintegrations per unit time. So in this case, we can say that the activity of a decay defines the rate of the decay. It defines how much of the atom or the radioactive substance disintegrates per every time. It is directly proportional to the number of atoms present. So a radioactive atom or radioactive compound with more radioactive elements would disintegrate at a different rate as compared to a radioactive compound with less radioactive elements. This activity of radioactivity can be calculated. So the activity, which is represented by the letter A, is given as the rate of disintegration times the initial amount of the radioactive substance present. We can integrate this, and the integrated equation will be given as activity, which equals to A naught natural log of negative lambda T, where A is the number of disintegrations at a given time, A naught is the initial number of disintegrations or the initial activity, and lambda is the decay constant and T is the time. So as we stated in our previous slides, 1 curie is represented by 3.7 times 10 to the power 10 disintegrations per second. And we shall apply this as we go forward and do certain calculations on activity. So let's look at this solved example, which says that the phosphorus isotope P32 with half-life of 14 days is used in biochemical studies to determine the pathway of phosphorus atom in living organisms. Its presence is detected through its emission of particles. A. What is the decay constant for P32 expressed in the units per second? B. What is the activity of 1 milligram sample of P? C. Approximately what mass of P will remain in the original 1.0 milligram sample after 52 years? Now, to solve for A, we are to find the decay constant, and we are to find it in per second. However, our half-life has been given in days, so we need to convert our half-life to seconds. We know 1 day equals 24 hours, and so we'll convert from 1 day to hours, then we'll convert from hours to seconds. So we begin by 1 day, which equals 24 hours. 1 day equals 24 hours. So 14.3 days will be, let's see, x hours. So we use ratio and proportion to solve for x, where 1 day will multiply x, So cross multiply. 1 day will multiply x, and 14.3 days will multiply 24 hours, and we solve for x. So when we simplify, we will get s to be 343.2 hours. We need to further continue to convert the hours to seconds. We know every 1 hour equals to 3,600 seconds. If that is the case, then 342.2 hours will be, let's say, x seconds. So we cross multiply, where this multiplies the hours, multiply the second, and the hours from this side multiply s. So we solve for x, and at the end of the day we'll get x to be 1.23455 times 10 to the power 6 seconds. Now, having solved for that, we know half-life is given by 0.693 over the decay constant. So decay constant will be given by 0.693 over half-life, and if we substitute the half-life into the equation, we end up getting 5.609 times 10 to the 09 times 10 to the power -7 per second. So we have successfully addressed the question A. Now let's move to the B, where we are to find the activity. So in the B, where we are to find the activity, we know that the activity is given by the decay constant times the number of atoms that decay per unit time. So we need number of atoms that decay, which is the n, multiplied by the decay constant, which we have calculated in A, to get the activity. But in this question, we have been given the mass of the sample, not number of activities. So we need to convert the mass of the sample to number of atoms. We have been given the mass of the radioactive substance instead of number of atoms that decay. So we need to convert the mass given to number of atoms. Now we know that number of atoms is given by the mole of atoms times the Avogadro's constant. So this is the Avogadro's constant, 6.02 times 10 to the power 23 per mole. So first of all, we need to find the number of moles, and number of moles is given by mass over molar mass. So if we can get the number of moles from the mass given to us, then we can multiply it by the Avogadro's constant to convert it from mass to number of atoms. So in these slides, we are continuing from our previous slide, and we've established that we need to calculate the number of moles. So the number of moles is given by mass over molar mass, and molar mass is always in grams per mole. So we need to convert our mass to grams before we can calculate in correct units. So our mass, which was 1 milligram, will be converted to 1 gram, which is going to be 1 times 10 to the power -3. So we have converted our mass to gram, divided by the molar mass, and that is going to give us 3.125 times 10 to the power -5 mole. Having established that, we can now calculate the number of atoms, which is given by the mole times the Avogadro's constant, and that's what we have established here. Then we can go ahead to, and that is going to give us 1.881 times 10 to the power 19 atoms. So we can now calculate our activity, which is given by lambda n, lambda which we calculated from the first question, that's A. So we multiply our 5 times 10 to the power 5.609 times 10 to the power next 7 by 1.881 times 10 to the power 19, and we are going to have an activity of 1.0552 times 10 to the power 13 atoms per second. Now we can go ahead to calculate our amount that will be left after 57 days, and we use ln nt over n naught equals lambda t. The t is the time, which is giving us 57 days. We need to convert it from 57 days to seconds, and by conversion the 57 days will be equivalent to 4.9248 times 10 to the power 6 seconds. So we can now substitute everything into the equation, and we are going to have ln nt, the nt which we are looking for, over the initial amount, which is 1 gram, 1 times 10 to the power negative 3 gram. That's, we've converted it from milligram to gram, times negative 5.609 times 10 to the power negative 7 times the time, which is 4.9248 times 10 to the power 6. By simplifying it, we will get the initial amount of the phosphorus 32 to be 6.3 times 10 to the power negative 5 grams. Let us look at transmutation. Transmutation can be defined as the conversion of one chemical element or isotope to another. An example is the conversion of potassium 40 to argon 40. So potassium 40 has a mass of approximately 40, and argon also has a mass of approximately 40, but potassium has an atomic number of 19 and argon has an atomic number of 18. So in the decay of potassium to argon, one proton is converted to a neutron in that process, and this decay of potassium to argon forms most of the argon in the air. Although transmutation is caused by either decay or nuclear reaction, not all these decay or nuclear processes can cause transmutation. There are two types of transmutation. They include natural nuclear transmutation and artificial nuclear transmutation. With the natural transmutation, it occurs, or is said to occur, when unstable radioactive nuclei is transformed to a stable one over a period of time. Example of natural transmutation, we can talk about the natural transmutation by stellar nucleosynthesis, and this creates most of the heavier chemical elements in the universe. We can also talk about when certain radioactive elements present in nature spontaneously decay by a process that causes transmutation, such as alpha or beta decay. An example of natural transmutation will also be the transmutation due to cosmic rays bombardment of elements, for example, to form carbon 14, and also occasionally it occurs from natural neutron bombardment. With regards to artificial transmutation, it occurs when an atom is struck with fundamental particles. So you bombard one nuclei with another atom or particle, and that causes it to disintegrate or to be transformed from one form to another. An example of artificial transmutation is transmutation which may occur in machinery that has enough energy to cause change in the nuclear structure of elements. Also, the conventional fission power reactor also causes artificial transmutation. This transmutation is not from the power of the machine, but by exposing elements to neutron produced by fission from an artificially produced nuclear chain reaction. Artificial nuclear transmutation has been considered as a possible mechanism for the reduction of the volume of hazardous waste or hazardous radioactive waste. So when particles are used to bombard this radioactive waste, it can probably convert them to another form which is more stable and safe. Let us look at balancing natural and artificial transmutation reactions. Now, the key to balance these reactions is the law of conservation of mass. So the masses on the right side of the equation should balance with the masses on the left side of the equation, and the atomic mass, the atomic number on the right side of the equation should also balance the atomic number on the left side of the equation. Let us try to balance these few nuclear equations. So with the first one, we have aluminium plus the helium to give us phosphorus and a neutron. Now, to balance this, you look at the atomic mass of aluminium and that of helium. When we sum the atomic mass of aluminium and helium, it should be equal to the sum of the atomic mass of phosphorus and neutron. So when we come to the solution here, you realize that the aluminium has an atomic mass of 27 and helium of atomic mass of 4. So we have 27 plus 4 here, and that should be equal to the atomic mass of phosphorus, which is 30, plus atomic mass of neutron, which is 1, and that is 30 plus 1. So 27 plus 4 is 31, 30 plus 1 is 31. So it means that the atomic masses of on both sides of equation 1 are balanced. Then we come to the atomic number. You realize that we have aluminium to be 13 and hydrogen to be 2. So 13 plus 2 should give us 15, and that should be equal to the sum of the atomic mass on the right, which is 15. So the atomic mass is balanced. So in all, we see that the equation 1 is balanced. Then when we come to equation 2, we have the mass of beryllium to be 9 and that of hydrogen to be 1. So in all, we have a mass of 10. When you come to the right hand side of the equation, you have lithium with a mass of 6, but the mass of lithium, which is 6, is less than the mass of beryllium and hydrogen on the left. So we need to bring in a particle that will balance the mass, and in doing that we need the helium, the helium atom, so more or less an alpha particle. So when you bring it in, the alpha particle has a mass of 4, so that 4 mass plus the 6 of the lithium will give you 10, which will balance the masses on the left and the right. And the proton, the atomic number, will also probably be balanced because beryllium has 4, hydrogen has 1, which is 5, and lithium on the right has 3, and the alpha particle, the helium atom that we are bringing in, definitely has 2. So it's going to be 5 also. So this is helium, this is He. These are self-assessment questions which I would want you to go through them and look at them, try to solve them to practice more.